Hey everyone, thanks for being here. Let's get started with today's webinar. I'd like to welcome everyone. My name is Jack Murphy, and I am the executive editor here at the Architects newspaper. Welcome to today's webinar, Facade Automation Technology for Public Building Projects, a CE Strong webinar powered by the Architects newspaper. And today, this webinar is sponsored by WindowMaster. This program is registered with the AIA CES for continuing professional education. Questions related to specific materials, methods, and services will be addressed at the conclusion of the presentation. The webinar is recorded and can easily be replayed when re-registered on the same webinar page, the same registration page. And please allow 7 business days to process a certificate of participation and AIA credit reporting for this presentation. So I'm excited about the webinar. In this webinar, you will learn how to describe occupant health and wellness benefits of automated natural ventilation technology for public building occupants, describe how intelligently controlled window and vent automation can reduce energy consumption and carbon emissions in public buildings, describe how automated windows and vents for passive smoke and heat evacuation can maintain safer egress from public buildings in the event of a fire, and describe the key elements of an automated window and vent control system and recall associated building design considerations. So throughout the course of the webinar, if you have questions, I encourage you to ask them using the Zoom Q&A button at the bottom of your Zoom window. There'll be time at the end of the webinar to get to those questions and have them answered. So now I'd like to introduce you to today's presenter, Peter Cater. And Peter has 18 years experience in the facade industry. He joined WindowMaster Clearline as its sales director in 2022. Peter is an engineer who brings extensive international facade product sales experience and technical expertise to WindowMaster's growing automation hardware and control systems business. He is committed to providing optimized solutions that create impactful real-world benefits for commercial and public building stakeholders, but also for the environment using WindowMaster's innovative and intelligently controlled natural ventilation technology. So again, please leave your questions for Peter in the Q&A window. We'll get to them at the end of the presentation, and I'll hand it over to you, Peter, for today's webinar. So thanks everyone for being here.
Thank you, Jack. Appreciate the introduction. Can everybody see my screen now? Jack, is my screen showing?
Not yet, Peter.
So I need to share it, right? Okay.
Great, that works.
Terrific. All right, so today's presentation, as Jack pointed out, is about facade automation technology for public building projects. It's worth 1 AIA learning unit credit, and I'll just hop into the summary of the course description and learning objectives. Jack already described the learning objectives, but I wanted to reiterate the summary here that window and vent automation systems offer a wide range of benefits for most building types. These include occupant health, wellness, and productivity, reduced mechanical ventilation energy consumption, safer egress during fire events, and compliance with ADA requirements. We're discussing today the applications and the associated benefits of window and vent automation systems for public building projects. So what is a public building? Well, the definition is pretty straightforward. It's any building that's generally accessible to the public, such as schools, daycare centers, museums, airports, hospitals, stores, convention centers, government facilities, libraries, and any other building which is not an industrial or residential building. Public buildings are important. They make up around 16% of all non-residential buildings in the US. And they're essential to every city because they play important roles in the community. People gather, children play, education happens, patients heal. Public buildings perform these and other essential roles for communities around the world. So it's crucial for these buildings to be as sustainable, healthy, and safe as possible, and to design them with innovative technologies that provide meaningful benefits for the occupants and the communities that they belong to, and also the environment. So there are three basic categories of applications for facade automation. The first being natural ventilation. Natural ventilation regulates the indoor climate of a building, and it uses the natural forces created by temperature and pressure differences between the inside and the outside environments. And these driving forces include primarily thermal buoyancy, or the stack effect, and also differential wind pressure at different locations around the building envelope. The system can be also activated by inputs from temperature and humidity sensors and CO2 level sensors within rooms to optimize the indoor air quality. The second category is mixed mode ventilation. Now, this is a combination of natural ventilation and mechanical ventilation. And this can either be where there are different periods with either one or the other operating, or periods where both natural ventilation and mechanical ventilation systems operate together to optimize the indoor air quality and achieve energy savings. The third category is smoke and heat evacuation, and this is where smoke and heat from a fire are extracted from the higher levels of a building using the operable windows. And this maximizes the time that egress routes and fire service access areas can be safely used during a fire. The basic principles of natural ventilation include three primary types. There's single-sided ventilation. This is, I guess, the least useful because it limits the amount of air exchange with the exterior environment that can be achieved. Typically, it relies on having a window which opens at a higher level and allows air to be drawn out through the window, typically through a local stack effect. Second category is called cross ventilation. This is where you have openings on opposite or different elevations of the building, and this creates cross ventilation in the room. This type of ventilation is powered by differences in wind pressure on the facade between the different window openings. So it pushes air horizontally through the space. The third category is called stack ventilation or stack effect, which utilizes the buoyancy force of warm air, which rises towards the upper level and draws in cooler air at the bottom. And this typically is used to drive air through the building in a vertical direction. These different modes can be used in combination with each other and optimized for the whole building. Some basic design guidelines when you're thinking about including a natural ventilation system in your building design. And these include a sufficient ceiling height, typically 8 feet or more is ideal, particularly for single-sided ventilation. The room depth with single-sided ventilation shouldn't be more than about 2.5 times the height of the ceiling, and never more than about 30 feet to have a meaningful effect. Cross ventilation, the distance between the operable windows on each elevation shouldn't exceed about 5 times the height of the room. The stack ventilation, the horizontal distance between the windows on the facade and the skylights, which exhaust the warmer air, shouldn't be more than 5 times the height of the room. So they should be aligned relatively closely in a horizontal distance, not more than 5 times the room height. Highly placed windows in the facade should be at least 8 feet or more above the floor, with sufficient clearance between the top of the vent and the ceiling. This is for inward opening bottom hung vents, so that you don't obstruct or limit the usable opening area which air flows in or out through. Optimize the use of night cooling. This is where the natural ventilation system opens the windows at the coolest time of the day, which is pre-dawn typically. This has the effect of pre-cooling the interior of the building. And that means that the mechanical ventilation system or heating system or cooling system doesn't need to be turned on until later in the day, because you've pre-cooled the building, I should say, just the mechanical cooling system. This is especially effective in buildings with a high thermal mass, which can use that pre-cooling effect for longer during the morning hours of operation or occupancy of the building. And lastly, space out adjacent automated windows where possible, so that you can utilize the free area at the sides of the windows, the triangles, if you like, as well as the bottom rectangle. That means if the windows are hard up against each other horizontally, those side areas of the window when it's open are right up against each other, and the adjacent operable panels don't leave enough space for as much air to flow through the side areas of the opening. Typically, you'll only get air flowing in through the bottom, in the case of an awning window, the bottom rectangular area. So by spacing the windows out, you get a much bigger potential free area, open free area for the air to flow in and out through. And override switches should be provided so that users and occupants can operate the windows manually through wall switches or key switches for the facilities team. And these switches should be placed close to the automated windows that the switch operates. So thinking about designing the natural ventilation system as a whole is very important, and not just the windows themselves. There's a bunch of different aspects that synchronize or work together to make the system work efficiently as a whole. These include outside temperature and rain sensing, wind speed and direction sensing, heating system feedback and communication with the window natural ventilation control system, and then a link to the building management system, if there is one, which enables a highly configurable design for the overall system so that it optimizes the efficiency and effects of the system. The types of sensors that you'll typically need for this type of system, and these all connect into the control system for the natural ventilation actuators. And these include, as I said, wind speed and direction sensing, rain, temperature outdoor, temperature and relative humidity indoor, also the CO2 level indoor. That's an important one, particularly for meeting rooms and classrooms and so forth. And then a link with the mechanical heating system to provide information telling it what to do and when. Typically what we'll do during the design phase for a new building, or even for refurbishments as well is a CFD analysis. We'll simulate the wind speed and direction around all the points of the compass and determine what the wind pressure would be, positive or negative, and how much pressure there is at each opening or operable window location for a given wind speed and direction. The hardware that we use to implement a natural ventilation system in a building, the primary device is called a chain actuator. You can see them here in this image. The chain is housed in a body with a motor in it, which drives the chain in and out of the body, and the chain's attached to the operable sash of the vent, causing it to open and close as the chain moves in and out. These chains are unidirectional. That means they only bend in one direction. But because the body of the actuator is fixed and the point where it attaches to the sash is fixed, they operate as if they were a rigid element, even though when the chain retracts, it can curl up inside the actuator body for storage. So the actuator is basically just an electric motor driving a chain in and out of the body, as you can see here. The actuator has to be provided with power and control signals, and these come from a control panel. Typically, that's a wall-mounted cabinet like this, which is typically 120 volts. And then the low-voltage DC cabling to the actuator supplies 24 volts DC typically for the motor of the actuator. There's typically also a third wire, which is for data communication between the control panel and the actuator. This provides the ability to read the position that the actuator is in other words, how far open the window is at any point in time, and also for coordination between actuators. For example, if you have two actuators on a window that's too big for just one, they have to synchronize with each other so that they don't get out of sync. And then thirdly, there's a connection between the controller and the building management system, if that's available. Now this allows the building management system to read information about window positions and so forth when the natural ventilation system is operating. It also enables commands from the BMS to be sent to the window control panel to customize its operation. The typical communication protocol between a BMS and a window controller is typically a BACnet IP data communication protocol. An alternative is KNX, but mostly it's BACnet in North America. Each actuator comes supplied with a pigtail cable, which is attached to the actuator. Typically, it's anywhere from 5 to 16 feet long. And this is connected typically from the actuator up to a junction box, which takes the pigtails from other actuators and then home runs them back to the control panel. You can have multiple actuators connected to a control panel, and then within the actuators connected to that panel, you can group them to operate in distinct groups. Typically, if you've got like a typical 1 amp actuator and say a 20 amp control panel, you can have up to 20 windows, single actuator windows operated by a single controller. Yeah, the types of information that communicated back and forth between the controller, the actuator, and the BMS include positional feedback and control signals. Operational speed that can be configured and monitored. Motor synchronization, which is where you have 2 or more motors on a vent that have to synchronize with each other, and an anti-entrapment function, which reverses the actuator briefly if it encounters an obstacle or a foreign object that gets trapped in the window. And you can also have a communication channel via a network that can be accessed remotely, which means that we can actually configure the operation of the actuators remotely by simply logging into the network and communicating with the controller. The types of automated, or I should say operable windows, which can be automated with chain actuators, the ones that you normally see on public buildings: top hung awning type, bottom hung hopper type, typically inward projecting, side hung casement windows. You can automate parallel pop out vents, curtain wall facade, for example. Skylights, that's an important one, particularly for smoke and heat evacuation. You can have center pivot windows and louver systems. So we have a different actuator that operates the louver system. Typically, that's a special type. There's one window type that's not shown here, and the question for everybody is which type is not shown here, since it's not suitable for automation using a chain actuator. And there's a hint that I'll give you here. It's typically used in residential buildings rather than public and commercial buildings. If you haven't guessed it already, the answer is it's the double hung window. Chain operator can't be used to automate a double hung window, but they're typically only used in residential projects anyway, so it doesn't usually come up. The actuator can be installed in two different ways, and we actually have different actuator models. There are different actuator models that are designed for these different installation methods. The top two pictures show a concealed mounting configuration where the actuator is installed within the frame profile of the sill and is concealed within that sill. So you don't actually see the body of the actuator. You just see the chain as it extends to open the window. And you can do that on aluminum and timber windows. It's a little different for each. Typically, this is where you have a very strict aesthetic requirement not to have a visible actuator. And it's obviously more expensive and a little more complex to design this, but it certainly can be done. These would typically be installed at the glazing contractor's workshop before delivery, or the window manufacturer's workshop before delivery of the window to the site, because they typically wouldn't be installed in the field. The bottom two diagrams show surface-mounted actuators. This is where the actuator is actually mounted in a visible position on top of the sill, and that's by far the most common mounting technique that's used. And this can be done in the field, which is the most common situation. Can also be done in the workshop. You can actually use surface-mounted actuators on both aluminum and timber windows, but also other types, typically fiberglass, for example, and in some cases vinyl. Vinyl's not as rigid, so it depends on the profiles that the windows are made of. Typically, if you want to have a surface-mounted actuator, but you have this requirement for the actuator to be concealed, there's another option, and that's to fabricate a sheet metal cover, which is typically painted to match the color of the window frame, that would extend the full width of the frame and conceal the actuator. This can also double as a support for a bug screen if bug screens are installed, so that the chain can still operate the window without having to pass through the bug screen. This slide talks about renovation projects where you're retrofitting an existing or historic building with a natural ventilation system. So you're putting these actuators on the windows. You can see on the right the actuator operating that hopper window there. The advantage of this over retrofitting the building with a mechanical ventilation system is you don't need space for air ducts within the building because the air is coming in through the operable windows. The only ducting you need really for the natural ventilation system is conduit for the wiring. That can be easily concealed and doesn't take up much space. So it provides benefits for the aesthetics of the renovated building versus trying to mechanically ventilate it. So there are a number of benefits that come from using a natural ventilation automated system. Energy is a great reason because the energy savings can be quite large. There's also a number of other benefits which are available with the use of a natural ventilation, intelligently controlled natural ventilation system. So we'll talk about these benefits in the next few slides. So the things that need to be considered when you're designing the project, energy savings is a big one. You can typically get anywhere from 30 to 70% in mechanical ventilation energy savings. And this occurs because when the exterior conditions are conducive to operating the natural ventilation system on its own, the mechanical ventilation system can be completely shut off during that time. And depending on the climate where the building's located, that can be anywhere from 30 to 70% of the time. And switching between the two ventilation systems can be programmed to occur automatically. So when the conditions become amenable to natural ventilation, the BMS will typically recognize this and hand over control to the natural ventilation system, and at the same time shut down the mechanical ventilation system so that natural ventilation can take over. And then, of course, when the conditions become unsuitable, the natural ventilation system will hand control back to the BMS and stop operating the windows. You can get anywhere between 20 and 70% reduction in carbon emissions, and this is associated with the mechanical ventilation system energy use. So that's another big reason why the energy savings benefit is very important for the environment, especially. Second category is health related. The indoor air quality, the indoor environment is very important for building occupants. And some of the benefits associated with natural ventilation in this regard include reduced occupant health costs, less visits to the doctor. You can get significant reduction in absenteeism when natural ventilation is used compared to sealed windows and a mechanical ventilation system, which recirculates the stale air. And you can also get a big reduction in sick building syndrome symptoms using natural ventilation as well. Productivity is the third one. And we see from various studies that you get a significant improvement in academic performance for students in classrooms when you have operable windows, naturally ventilated spaces versus mechanically ventilated spaces. You can also have large productivity gains in office environments. And typically the feedback from occupants shows a greatly increased level of user satisfaction with naturally ventilated spaces versus mechanically ventilated spaces. Finally, you get reduced costs with natural ventilation. You can get a return on investment in a very short period of time. The cost of the motors and controllers and associated wiring and installation are relatively small compared to the investment in a mechanical ventilation system, or a larger mechanical ventilation system than you would need when you have natural ventilation. You can have a much lower lifetime cost using natural ventilation, and this is obviously a very important thing for public buildings, which are sensitive to budget constraints. So this diagram is really just highlighting some of the benefits that you can get with natural ventilation in public buildings. Night cooling I've mentioned before, which is where you pre-cool the interior of the building using outside air at the coolest time of the day. And that means the mechanical ventilation system, the cooling system, doesn't have to be switched on till later in the day. This is especially applicable in warmer climates where you can't necessarily operate natural ventilation during the hottest part of the day. You can obviously get the reduced CO2 emissions associated with not having the mechanical ventilation operating all the time. You get the safety benefit with smoke and heat evacuation during a fire. By the way, that feature, that benefit, is available with natural ventilation systems. So the natural ventilation system can provide the fire safety benefit as well as all of these other benefits. It can be used for both. So it only functions as a smoke and heat evacuation system when the fire alarm system triggers that operation in the controller. You can have app-based control of the system on your phone, which makes it very convenient for building management staff to control and optimize the operation of the system. You get improved indoor air quality, obviously, in terms of particulates, particularly if you install a particulate sensor on the outside of the building that can be integrated into the system so that the windows won't open if there's pollution outside at a certain level that you don't want to come in. Thermal comfort's a big one. Acoustics is another benefit. You don't have the sound of the mechanical ventilation system inside the building constantly. Of course, in some environments, there might be traffic noise, which works against this, but in most cases, there's a net benefit as far as acoustics and distraction. And daylight, obviously, if you have bigger windows, you're going to get more light into the building. Reduced energy use, we've talked about before, and reduced cost, obviously, that comes with that reduced energy use. So here's a project example at the University of Baltimore School of Law. This is a completed project which was designed using natural ventilation with both cross ventilation and stack effect being employed to optimize airflows through the building and provide all these benefits of indoor air quality, etc., and energy savings. Now, in this particular project, they opted not to use like PV solar panels on the roof or solar thermal heating systems. Instead, they used a downsized mechanical ventilation system in combination with the intelligently controlled natural ventilation system, and realized a significant capital cost saving because of that smaller HVAC plant that was needed. The law center is consuming something like 30 to 40% less energy in its mechanical ventilation system than if that system was operating alone and had been sized to operate without natural ventilation. The Institution of Engineers, actually in building services engineers in the UK and other similar bodies around the world, agree that less recirculated air is a good thing, and higher fresh air rates are very beneficial for building occupants. So what we've seen are that naturally ventilating classrooms is directly associated with students' academic performance. And conversely, if the building is sealed and stale air gets recirculated, that leads to rising CO2 levels, and this is shown to negatively impact students' performance, increasing fatigue, impairing attention, and focus. The study was done on university students. So in the classroom environment, there are different features which can impact student performance, academic performance. We know that having big windows with more light coming in is beneficial. We found that there's significant improvement when you have operable windows that are automatically controlled to open. Indoor comfort is important, so temperature and humidity. This is controllable using the natural ventilation system. Students tend to move around the facility more efficiently. There's significantly reduced absenteeism, and you avoid this problem of CO2 buildup within classrooms, meeting rooms, etc. What they found is every 1,000 parts per million increase in CO2 concentration produces a 10 to 20% increase in student absence. So you get more absenteeism. And finally, you get a big reduction in sick building syndrome symptoms. You can see some of the symptoms over here on the right, from dizziness, concentration problems, fatigue, headache, irritation, nasal, and eye irritation, throat irritation, etc. And this chart shows that with natural ventilation, all of these symptoms are typically reduced versus with mechanical ventilation systems. So focusing on the productivity benefits for public buildings, office and school buildings, etc., you have significant improvement in performance, attention span, reduced absence, faster progression academically versus mechanically ventilated classroom, better test scores. Workers are more productive, substantially more productive with natural ventilation. And air movement, obviously, fresh air movement into the building produces significant benefits in terms of productivity. And also having occupant override control ability of the windows can also improve productivity as well. That's if there's a local effect that somebody doesn't like, they can operate the windows manually to mitigate that. You can see here when we compare the different aspects of building design that affect health. We're comparing here daylight, which is the yellow bars here. Indoor plants is one. These central area here, these bars are all with natural ventilation, and then window view. So while the other aspects are important, the biggest improvements here we see are in reduced symptoms of sick building syndrome with natural ventilation. And the studies that have been done consistently show a big benefit for natural ventilation in terms of sick building syndrome reduction. So this slide shows a project we did many years ago. It's a demonstration facility at Harvard University. It's called House Zero, and its purpose is to test and evaluate new technologies in buildings for reducing energy consumption and improving indoor air quality and various other things. This project rather was installed originally with intelligently controlled natural ventilation system, which works to optimize the indoor air quality and comfort throughout the year. The building itself doesn't have a mechanical ventilation system, and that's why it's able to be a net zero build. Research is ongoing in this particular building. In fact, all of the existing natural ventilation system is going to be replaced soon with an updated system to run a new evaluation of the benefits. As you can see here, the building relies on 100% natural ventilation to maintain indoor comfort, air quality, and minimize energy use. It also has all of these other great features, which all add up to help the building achieve its net zero goal. So I'm going to talk now a bit about the principles, components, and system integration of a natural ventilation system. This is the one at Harvard, at the House Zero project. The operation of the intelligently controlled natural ventilation system is integrated with automated sun screening and underfloor heating. The three systems operate together to optimize the overall indoor air quality and comfort in the building and minimize the energy consumption. The project uses both single-sided, cross, and stack ventilation in different parts of the building. There are 52 hopper windows, there are some skylights, and there's a solar chimney as well. Solar chimneys are used to maximize the stack effect as a way of drawing air through the building vertically, especially on sunny days. There are 23 indoor climate zones. This is a way of tailoring the system to optimize the indoor air quality and airflows through the building. These zones are created in the software which the controller uses to operate the windows. So you can have a zone which operates the windows on two opposite elevations of the building when you want cross ventilation to occur, or you can have a zone which operates the solar chimney, for example, to modulate the amount of air drawn in through the lower levels. The project has temperature, CO2, and humidity sensors in each zone, and a weather station, which is located on the roof, and that monitors the exterior conditions, including wind speed and direction, which helps to decide how much and when to open each vent location on the building envelope. Now, I'd like to talk a little bit about the fire life safety benefits. This is with automated smoke and heat evacuation. It's basically the same type of system as we use for natural ventilation. And in fact, as I mentioned before, natural ventilation systems can have this element of fire life safety benefits built into it as well. An example of this would be the Augusta University Cancer Research Center, which is a 72,000 square foot expansion of the existing building. And it uses operable windows and vents to provide smoke and heat evacuation in the event of a fire. For this project, the actuators were selected during the design phase as part of the building's heat and smoke management strategy by the contractor. The window controllers are connected to the building's fire alarm system. and also to the building management system. So this enables natural ventilation strategies to be used, as well as, in the event of a fire, the smoke and heat evacuation functionality. When a fire occurs and is detected by the fire alarm system, that system sends a signal to the window actuator controllers to open the windows, particularly the high windows or skylights, to vent smoke and heat out of the building interior. This reduces the interior smoke level that would otherwise obscure visibility of signage, emergency signage, egress routes, etc. So it improves the survivability of the building in the event of a fire. Once the actuators have been told to open the windows and done so, the controllers will then, using the data feedback wiring that I mentioned earlier, communicate back to the fire alarm system, confirming that the windows have reached their fully open position. That way, the fire alarm system knows that the smoke and heat's being evacuated. Code requirements affect the way we design buildings with natural ventilation technology incorporated into them. And this includes the requirements that apply to operable windows specifically. This includes things such as window opening limit, or the minimum opening area versus the floor area allowance. This, in turn, needs to be considered when you're designing a natural ventilation system, because it could limit the amount of free area that the windows will achieve, will be allowed to achieve. And that means also limiting the amount of fresh air that can be drawn in. In many commercial buildings, when the facade is multi-level, multi-story, the upper levels typically in many cities is limited to about 4 inches maximum opening. This is to stop objects falling out, or people falling out the windows. It's a safety requirement that typically doesn't apply on the ground level, but this also needs to be considered in the natural ventilation system design. The specification document is key in designing a building with natural ventilation. And although the hardware for the natural ventilation system is typically described in Division 8, which is the openings, obviously the openings division, there are other divisions that relate to other aspects of the natural ventilation system, which need to be included or have content added to them so that the system is properly specified. So, as I mentioned, Division 8 is really where the hardware lives, including the window controllers typically live here. Division 26 is the electrical wiring. That's typically doesn't typically require content specific to the natural ventilation system, unless there's some special wiring required. But typically for most systems, it's simply 120 volt supply to 110 volt supply to the controller, and then it's all low voltage 24 volt DC out to the controller. So there's not really any special wiring typically required. Division 25 addresses system integration, where you would connect a building management system, building automation system, to the natural ventilation controller. Division 23, which covers mechanical ventilation typically, or ventilation generally, is where you would typically put the content for the natural ventilation control system. Often Division 25 content's not needed, because you can put all of that integration in spec content into Division 23 as well. So typically we'll see Division 8 for the hardware, and then Division 23 if you have the intelligent control aspect of the system. So that's the end of the presentation. I encourage everybody to consider natural ventilation systems, particularly intelligently controlled natural ventilation systems for public building designs when these sorts of projects come up. For the reasons that I've given before, the benefits, as I've mentioned, are really quite substantial, and the cost of implementing the system is generally within most public building project budgets. So happy to answer any questions. I would be happy also to provide an email with a link to the presentation or arrange a meeting with anybody that wants to discuss it further. I think Jack said earlier that AN will provide a link to the presentation to all the attendees, so you should be able to access it through that link. If you do have any questions, then I'm happy to answer them. That's the end of the presentation. Thank you for your attention.
Thank you, Peter. I think that was super thorough. Again, if you have questions, we have a little bit of time left. You can put them in the Q&A. There's one here, I guess, about some of the louver products you were discussing. Can these louvers be used as external shading, or how does that equipment relate to shading on the facade of the building?
That's a great question, and in fact, the louvers that I referred to in the presentation are the type of louvers which are designed to admit air through the facade into or out of the building, and that includes smoke and heat as well. The louvers typically used for sun shading are typically installed attached to the exterior of the facade, and those are often fixed, but they can also be automated. The type of actuator that would be used to automate that type of operable sun shading louver system on the exterior of a curtain wall or storefront system would be different to the type of chain actuators that I've shown today, which are used to operate windows and skylights. The type of actuator I showed you that operates the louver system for natural ventilation is a different type. It's not a chain actuator, but it moves a pin that then causes the louvers to change their angle. That's typically not the type of operation system that exterior sunshade louvers have. These would typically have a linkage that is driven by a linear actuator, and that would typically be a weatherized product that goes on the outside of the building. So that would be a different category of hardware for that application, and it doesn't really relate to natural ventilation, other than the fact you can integrate the operation of the exterior operable sunshade louvers with the mechanical ventilation, with the natural ventilation system, I should say, so that the shading is optimized to work together with the natural ventilation airflow system.
Great. Another question, I think, related one, is how can flexible chain push open windows if it's used in compression versus tension?
Yeah, this question comes up a lot, especially at trade shows when people see the installed actuator opening and closing a window and obviously pushing the weight of the sash as it opens, and it behaves like a rigid element. Whereas when you see an actuator that's not connected to a window, the chain becomes like a floppy, typical, like a bicycle chain, I suppose, with one key difference: it only bends in one direction. So in the other direction, it only goes to its straight position. It can't bend the other way beyond being straight. Now, when you fix the actuator onto the window frame and you attach the end of the chain to a fixed point on the sash of the window, the chain effectively becomes a rigid element when it extends, because it can only bend in one direction, but it's constrained by the fixed position of the attachment point to the sash and the mounting of the actuator body on the window frame. so that it always stays straight. When it retracts inside the actuator body, it can bend in the direction that allows it to curl up inside the storage area within the actuator, and that's how you can have an actuator body that's shorter than the length of the chain. So that's how that works. It is a question I get quite a lot. And it's often the best way to understand it is to actually have a physical actuator that you can actually manipulate the chain and see how it works. That's something you can see at trade shows typically.
Got it. I want to go to, there's a question in the chat that I want to pluck out of there, which is about how do some of these systems work in humid climates, or how do you kind of design for, more humid climate zones when using this type of technology?
That's another great question. And in fact, not all climates are suitable for an intelligently controlled natural ventilation system. Down in Florida, the application for natural ventilation is somewhat limited because of the sheer number of days per year when it's very warm and humid outside, and you don't want that air coming in because it would obviously be uncomfortable. In that climate, there are two applications where controlled natural ventilation systems would have a benefit. One of those is with, as I mentioned before, night cooling, or what we call night flush, where the system draws in cool air at the coldest time of the day, which is typically pre-dawn, and pre-cools the building so that when it warms up outside and the windows are closed and the mechanical ventilation, the air conditioning system comes on, that can happen later in the day because of the pre-cooling of the building interior that occurred during the night. The second application that is used in climates like that is the smoke and heat functionality. And that's something which can be designed without having a natural ventilation component to it. So it really only operates when there's a fire emergency.
Thank you. Another question from the Q&A, can the actuators be connected in a daisy-chained fashion, or do they have to be connected directly to control panels? I interpret that as like, can they be in series and in parallel, or in just one configuration?
That's another great question. So it really depends. So if you've got a window that's wider than, say, 55 inches, you're going to need two actuators on that window to ensure that the gaskets are properly compressed at the corners versus having a single pull point, which doesn't necessarily close the corners sufficiently in a wide window. Now, those two actuators obviously have to be synchronized with each other so that they move exactly the same and don't get out of sync. So in that sense, those two actuators, you can also have up to 4 on a single panel if it's a really, really big one, all have to have a connection to each other. This is done through the cabling. And then there's typically a single connection then back to the controller for those up to 4 actuators on one window. Now, if you've got separate windows, each with a single actuator, and they're in a long row of windows, for example, typically what you'll have is the pigtail from the actuator on each of these windows is run up through the frame, typically to a junction box above the window. And this junction box connects to the next junction box, which connects to the next one or more windows. And then the wiring goes from the junction box in a single cable all the way back to the controller. So you don't necessarily have to have a single wire for each motor going back to the controller. You can have them combined in a junction box to a single cable, which then goes back to the controller. And that's when all the windows are grouped to operate together. If they all are going to operate independently with their own override switch, which is very unusual. Normally you'd have windows grouped in zones. In that case, you would need to have each actuator connected back to a motor line on the controller. but that's not the usual situation. Normally, you're going to have windows grouped together and combined using junction boxes, so you only have a single cable going back to the controller.
Got it. I know there are a couple more questions in the Q&A, but unfortunately, I think we're at the time for today's webinar. So for additional questions, Peter, you shared your email address in the presentation, and I'm sure you're happy to answer those as they come up or as you're reflecting on the presentation. So I want to say, just to wrap up, to say thank you again, Peter, for your expertise and for joining us. Thank you all so much for attending this live webinar, Facade Automation Technology for Public Building Projects, a CE Strong webinar powered by the Architects newspaper. And today's presentation was sponsored by WindowMaster. The webinar is recorded. It can be easily replayed using the same registration link. And please allow 7 business days to process certificates of participation and AIA credit reporting for this presentation. A big thank you again to our presenter, Peter Cater, and to WindowMaster for sponsoring this webinar. We hope to see you all again soon at a future event. So thank you so much and have a great day.
Thank you, everybody.